Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today we're looking at another important theorem. It's called the extreme value theorem. And again, by the end of today's lesson, or by the end of this, it's probably going to be a two-part video, you need to understand the initial conditions to be able to apply the theorem, and then understand the conclusion of the theorem, and then be able to apply it. So before we get into the actual theorem, we have to review two different concepts, relative extrema and absolute extrema. So take 60 seconds, write down the difference or what each one is in the box below. So what are absolute extrema and what are relative extrema? All right, so relative extrema are a maximum or minimum on a given interval of a function, right? Whereas absolute extrema are a maximum or minimum over the function's entire domain. So you have to look at the entire domain and figure out what the max value is, what the minimum value is. So we're going to do some practice with relative and absolute extrema as we lead ourselves into the extreme value theorem. So we have two graphs below, one of f of x, one of g of x, and they ask us some questions. Take a few minutes on your own, try to answer these questions, and then come back for a discussion. All right, so it says identify the coordinates of the relative extrema of f. So again, these are going to be our relative maximums and minimums. So we have -3, 0. We have -1, 3. And we have 2, -6. Then it says on the domain of f, what are the coordinates of the absolute extrema? Well, there is no absolute maximum, right? Because the function continues upwards to infinity on the x values get more negative and the x values get more positive. So there is no absolute max. But there is an absolute minimum value, right? And that's going to be this value right here. Absolute min at 2, -6. Let's answer the questions about g before we answer that last question, because it applies to both. So the relative extrema, we have -3, -4. We have -1, 4. And we have 3, 2. The coordinates of the absolute extrema, well, the highest value of the function, the largest y value occurs here. All right, so that's going to be 6, 5. So let's color coordinate it with the other ones. Absolute max at 6, 5. And our absolute minimum, you can abbreviate absolute ABS. Absolute minimum, not maximum. Turns out it's at this point right here, -3, -4. Okay. The last question says, on the domain of the given functions, did the absolute extrema occur at the function's relative extrema? So again, if we compare these points here with the points here, did they ever overlap? Were they ever the same? And our answer is sometimes, right? Sometimes the relative extrema ended up being the absolute extrema, but sometimes they didn't. If we talk about the graph of f of x, right, one of the relative minimums ended up being the absolute minimum, but the relative maximum did not end up being the absolute maximum. So sometimes they overlap, sometimes they're different. That's all we can take away. So now we have the same functions, but the questions are a little different. So again, pause the video for a couple minutes, see if you can answer those on your own. First question says, on the interval -2 to 3, the closed interval, what are the absolute extrema of f? Well, let's first talk about the absolute maximum, and we're going from -2 to 3. So -2 to 3. Well, we have an absolute max at, we're looking at this interval right here, that is going to be up here at -1 comma 3. Our absolute minimum is all the way down here at 2 comma -6. Then it says on the interval -4 to 1, closed interval, what are the absolute extrema? Oh, we got to erase this. So now we're at -4 to 1. Okay, our absolute maximum. Well, it looks like we have 2. Or maybe it's, nope, it doesn't. It's going to be right here. It's a little hard to see, but the function does reach all the way up here. So we'll have an absolute max at -4 comma 4. It is possible for there to be 2 points out of the absolute maximum, right? At first I was thinking that it looked like it was crossing -4 at that point and then that point, and it looked like they may be the same. But upon further inspection, they were not. But there could be 2 points that are both the absolute maximum. Absolute minimum, well, looks like it's going to be down here. Oops, wasn't drawing. Looks like it's going to be here at 1 comma -3. So absolute minimum at 1 comma -3. Let's go ahead and look at G. So our first interval is -4 to 5. Our absolute maximum is going to occur, okay, in here it does occur at 2 spots, right? So absolute max at both this point right here as well as this point. So we have -1, comma 4, and 5, comma 4. Absolute minimum, looks like there's only one of those. It occurs at -3, -4. So absolute minimum at -3, -4. Let's change our interval to -2 to 6. -2 to 6. Our absolute maximum is going to occur all the way up here at 6 comma 5. Absolute minimum, well, that's going to occur right here at 3 comma 2. So let's go ahead and wrap this up with our final question. When the domain is restricted to a particular closed interval, what are the 3 places that the absolute extrema could exist? I understand that sentence is not quite written grammatically correct, but what are the 3 places where the absolute extrema could exist? So think back through all of your examples. Where were those points located, and what was special about those different points? And I'll give you a hint. There are 3 things that we are looking for here. Well, the first one is that they could occur at the endpoints of the interval. the endpoints of the interval. And a quick example would be this maximum up here, right? Our interval was -2 to 6, and our absolute maximum was 6, 5. So they could occur at the endpoints. Another possibility is where the derivative is equal to 0. So examples here would be not over this interval, but when we had the interval -2 to 3 on my eraser, now I'm on my pen, we had our absolute minimum down here, right at 2, -6, and that would be a spot where the tangent line has a horizontal, or the tangent line is horizontal, which means it has a slope of 0. So sometimes your absolute extrema will occur where the derivative is equal to 0. The third place, let's use a different color, where the derivative is undefined. Right, because if we look over here at our graph of g of x, if we look at the interval, we'll go -4 to 5. Our absolute minimum was not where the derivative is equal to 0, because the derivative does not exist at a hard corner like that. But it did. The absolute extrema was at a spot where the derivative was undefined. So that's another possible option. You may say, why are we checking these, or why are we thinking about this? Well, this is going to play into the extreme value theorem, and we're going to have to understand where absolute extrema can occur for a function. Well, they can occur at the endpoints of whatever interval you're looking at. They could occur where the derivative is equal to 0 on that interval, or they could occur where the derivative is undefined. So we're going to hold on to these three things, and we're going to save them for some application problems later. Let's actually now write out what this theorem says. So it's actually less complicated, well, to write than the other ones. So if f of x is continuous on the closed interval a to b, then f of x has at least one minimum and maximum value on the interval. And they could have more, right? Because we could have a maximum and a minimum that have the same y value, and we'd have more than one. But we know at least there's going to be one of each. So let's now apply this to some problems. Let's see, which one do we want to do? And we're actually going to skip this problem. You are free to do this one on your own. This problem, this entire page actually, is also related to the top of this page. So on the previous page, you're looking at the same function, but it shows you what it is graphically on the interval -4 to 1, and then you're going to be working strictly with it algebraically on this other page. What we are going to do is start off with three functions, and all we're going to do is determine whether we could use the EVT, the extreme value theorem, to state whether there is a maximum or minimum value on that interval. So take a few minutes, pause the video, check and see if those functions are continuous on the interval -5 to 0. So if we look at that first function h of x, we can see that that denominator is going to equal 0 when x is equal to -3. And then we can check to see if -3 is on the interval, which it is. So we are not going to be able to use the EVT on this interval for h of x because it's not continuous on the interval. And we just need to state that, right? We need to say EVT not applicable for h of x on the closed interval -5 to 0. because h of x is undefined at x equals -3. So it's not continuous on that interval, -5 to 0, closed. If we take a look at g of x, this function has a radical in it, so we need to just look at where the quantity underneath the radical is negative. That would be where this function does not exist, or where it's undefined. And we can see that any number less than 3 is going to make this function undefined, right? Because we're going to get a negative number underneath the radical. And to be honest, -5 to 0, right? This interval up here, none of those numbers are going to make g of x defined. So g of x doesn't even exist on that given interval, so it's certainly not continuous, right? A function has to exist for it to be continuous. So again, we would say the same thing. EVT not applicable for g of x on the interval -5 to 0, because g of x is only defined on the interval 3 to infinity, right? Any number 3 or larger, g of x works. Any number less than 3, it is undefined. All right, let's look at this last one, f of x. We have to know something about the natural log function. If we think about what the graph of the natural log function looks like, so it has an x-intercept at 1, and it has a vertical asymptote at x equals 0, which means we can only have positive numbers inside of those parentheses. Right, so the input to a natural log function, and remember, this is natural log of x, not natural log of the quantity x plus 7, but it still gives us the same idea, right? Whatever is inside of those parentheses cannot be 0 or negative. It has to be a positive number. So again, we have to think, okay, what values of x are going to give us something negative or 0 underneath or inside the parentheses? And, well, it's anything -7 or less than -7. So -7 or anything less than -7 will not work, which means our domain here is -7, not including -7, to positive infinity. So we can see that this domain does include the entire interval -5 to 0. So we could explain here. And if you're on an FRQ, all you would have to do is say that this function is continuous on the interval, thus the EVT is applicable. I'm going to write something a little bit more here just to help us understand why it is continuous, but just note that you would just need to state that it's continuous to use it on an exam. I'm going to say here f of x is defined and continuous on the open interval -7 to infinity. Thus, it is continuous on the closed interval -5 to 0, and the extreme value theorem, or the EVT, is applicable on that closed interval. And again, if you were on an exam, you would just need to say f of x is continuous on -5 to 0, and thus the EVT is applicable on that closed interval as well. Okay, we're going to finish this video off with one example where we have to put everything together. So I'm going to erase this and we're going to go down to number 1. It says, given the functions below, determine the absolute extreme values of the function on the given interval, provided the extreme value theorem is applicable. If it is not, state specifically why it is not. So we're going to look at number 1. Well, we can think about whether the function is continuous on -1 to 3. And it is a polynomial function, so it is going to be continuous. So we're first going to say 1, f of x is continuous on the closed interval -1 to 3. So EVT is applicable on the closed interval -1 to 3. So we've stated the initial condition, we've stated that it exists, and now we can go about finding whatever those extreme values are. We have to try to find the absolute maximum on the interval as well as the absolute minimum. Here's where those 3 ideas from earlier come into play. They're the 3 places we have to check. We have to check the endpoints of the interval. And those are what I like to check first, just to get those out of the way. So I need to check, and I'm going to label what I'm doing. So I'm going to check the endpoints. So I have f of -1. And regardless of whether this is a calculator problem or a non-calculator problem, you could just state what it is. You don't have to run through all the algebra. We end up getting f of -1 is equal to -2. And f of 3 is equal to actually -2 as well. So we check the endpoints. Now we also need to see if there's any points where the derivative is equal to 0 or where it's undefined. So I need to take the derivative of f of x. So f prime of x is equal to 3x squared minus 4x minus 3. And looking at this now, this would be a calculator problem because the values at which the derivative is equal to 0 are not integers, so they would expect you to use a calculator. We need to check out where this derivative is undefined, which is never because it's a polynomial function. And then we need to check where it's equal to 0. So I'm going to set it equal to 0. And then you could graph this in your calculator and just figure out those x values. It turns out that one of them, x, is approximately -0.535. That is both rounded or truncated. And the other one, so I punch this into my calculator real quick. We have x is approximately equal to 1.869. That is rounded, not truncated. So those are my 2 x values where my derivative is equal to 0. I'm looking for absolute extreme of those, so I'm looking for y values. So I now need to substitute those into my original function to figure out what the y values would be. So I'm going to have f of -0.535, and that's going to be, actually I'll write the other one out here first too. Then I'm going to have f of 1.869. And again, I can go punch those 2 values into my calculator and come back with the answer. I get approximately moving my page. I get approximately -1.121 rounded. And for my 1.869 value, I get -8.065, also rounded. So here are the actual values I need to compare. And I have 2 values in black. I'll unbox these. I have 2 values in black and I have 2 values in purple. And I need to know what's my absolute max and what's my absolute min, because I've tested every single value that's an option. Well, my absolute maximum is right here. negative 1.121 approximately. And my absolute min is right here. So again, sometimes they'll be the endpoints of the function. In this case, they turned out to both be values where the derivatives were equal to 0, or relative mins and relative maxes as well on this interval. So this is the entire process that you would need to go through if you are trying to figure out what the absolute or what the extreme values are of a function over a given interval. So there are 3 other problems to practice on this page. Same process. First, decide whether the extreme value theorem is applicable. If it is, then go check those 3 points, right? Check the endpoints, the y values for the endpoints. Check the y values when the derivative is undefined, if there are any. And check the y values for where the derivative is equal to 0, again, if any. Okay, that's going to wrap it up for this video. Enjoy the rest of your day, and I look forward to seeing you next time.